Dear students, welcome back. In the previous lecture, we had seen all the types of first order differential equations which will admit closed form solutions, and we had also promised that we will do both closed form solution type ODEs and approximate methods. We have already seen one type of approximate method, which is the Picard's iteration process. In this lecture, we are going to see another type of approximate method, basically the graphical method, which is the method of isoclines. Okay, so to begin, let's introduce the notion of what is called the integral curves. Okay, what are integral curves? See, when you have an ODE of some form, so any order, let's say kth order, right? You have y prime y x equal to 0. Then the unknown is the function y and all its derivatives. So the unknown is actually a map from the domain I to R, right? Which means the y can be geometrically viewed as some curve in R2, right? So the y could be, we have already seen, it's some family of curves, right? So it's some curve in R2, so it could be anything. So this is xyx, which is a curve, and we have already seen when we saw the notion of explicit solution and implicit solution. It's not always, the curve is not always a graph of a function. Locally, yes, it's a graph of a function, but you could also have family of curves like this, right? So you could have a family of circles, which are the solutions, right? In this case, they are not, they are curves, they are not graphs, but they are locally graphs. So what we are trying to say here, as we have already seen before, so we are just recalling that the solution of an differential equation is some curve in R2, right? Because you are dealing with a function which is one variable and real valued. So it's a curve in R2. Fine. So when you look at the first order ODE, when we took the special form of ODEs where there is linearity in the highest order, which is y prime in the first order. So when you say y prime equal to fxy, and for this ODE, because it's first order, we have a one parameter family of curves as solution, right? And right, so the solutions are one parameter family of curves, which is something which we have already seen so far. So what is the solution? The y, right? And what is this relation saying? This relation is giving, so this differential equation is giving you a relation between the derivative of y and some known function f. And what is this derivative of y? It is the tangent of the unknown y. So y prime, so if y is unknown, what is y prime? Y prime is the tangent to that curve y, right? So what is given to you is some information about the tangent of the curve that you want to find, right? Whenever you take ODE of this form, that's what is given. What is given is some information on the tangents of the curve at every point. Okay, so what we are looking for when we say we are looking for a solution of this ODE, what we are looking for is a y. And what is that y? The y has this property that its tangents are nothing but fxy. So at every point xy, or in other words, at every point x0, y0, the unknown curve y has its tangent, the slope of the tangent is fx naught y naught. So you are looking for a curve y whose slopes at every point is fx naught y naught. Okay, such a curve is called integral curve. So basically, when we say we want to solve this ODE, we are looking for integral curves corresponding to this differential equation. Okay, so what does integral curve means? It's precisely that curve whose slopes are given by this f appearing in the PDE. Right, that's what this ODE is telling you. So this is a very special form of ODE. Right. So just to recall again, this ODE is telling you a relation about so the unknown is y, this y, and this ODE is a relation between the slope of the tangent at any point of the curve. This is the relation, right, where the slope is known. So at every point you know the slope, and then what will be the curve, right? That is the question that you are answering when you try to solve this ODE. Okay. For instance, as we have already seen in some earlier lecture, we have even drawn the graph of this. So when you take this ODE, we had already computed that the family of parabolae are the solutions to this ODE, and these are the integral curves. So in this case, f is 2x, right? So what is this saying? So you are looking for that family of curves where at every point the tangent, so slope of the tangent is 2x. Okay, that's how you will. So this interpretation, so this point of view of the differential equation and the solution is going to help us do what is called a graphical method, basically an approximate method where even if we don't know the closed form solution of the differential equation, one can kind of sketch the graph or sketch the curve in R2, okay, using this information that there is something about the slope of the tangent. Okay, so how do you do that? So you note that once you have a family of solutions, f, x, y, c, right? Usually family of solutions are of this form, right? It's a function of x, y, and some constant, right? Of some ODE, which is a first order ODE. So we have only seen some special cases where we can compute exact solution. Otherwise, solution is not computable. I mean, it's not, you usually don't have a closed form solution always. Okay, but you know if it is solvable, there is a family of solution, and if it's first order, it's a one parameter family of solution. So this ODE, this gives you an information. So this gives you the slope fxy of the integral curve at point xy, right? So you are in R2, you want to find some y, okay? You don't know what this y is, but what you know is that at every point, the slope of the tangent, right? At every point, the slope of the tangent is fx naught y naught. Okay, at every point, this is, so if this is some other point x1 y1, it's x1 y1. Similarly, if this point is fx2 y2. So at every point, what you know is the slope of the tangent, and using that you need to find the curve. That's what this first order differential equation is about. For instance, if you take this ODE, y prime equal to 2x plus y, it has slope 4 at the point 1 comma 2, right? Because what is fxy? Your fxy is 2x plus y. So at 1 comma 2, you know the slope is 4 because f of 1 comma 2 is 4. In fact, you can do, you know the slope at every point here. For instance, let's take the point 0 comma 0. So at 0 comma 0, x is 0, y is 0. So f of 0 comma 0 is 0. That means at the origin, the slope of the tangent is 0. Okay, so this is one information. In fact, you can go further. You can look at all the points where the slope is 0. How do you know that? So when will the slope, so find out all x and y such that f of xy is 0. And when will that happen? Whenever 2x plus y is 0. So whenever y is minus 2x. Right? So basically, if you take all the points on this line, y equal to minus 2x line, right? On this, for all these points, so for all the points on this line, the slope of the curve is 0. So that's how you solve. Similarly, if you solve fx comma y equal to 1, you get the curve on which the slope of the tangent is 1. In fact, if you replace this with any c, then you can get the curve along which the slope of the curve of the unknown y is c. Okay, so this is something. So with this information, just this differential equation, using this differential equation, you have this slope of the tangent at every point for the unknown curve, right? And if you know the slope of the tangent at every point, you just draw a curve such that you have a tangential, so you have a tangential intersection at these points of that slope. Then you can actually plot the curves, right? I will show it by examples, but the understanding is that even if you don't have an exact formula to solve for this ODE, the ODE itself can give you an approximate way to visualize the graph or the shape of the curve. Okay, shape of the unknown solution y. So how do you do this? So since, as I pointed out, at every point x naught y naught, you can compute the slope. At every point, you draw a small line element of the corresponding slope. In this case, it's 4, but at every point x naught, y naught, you have the slope f of x naught, y naught, right? In this example, it's 2x naught plus y naught. So whatever number that you get, you draw a small line element of that slope. Okay. Now do this at all points, then what you get is a direction field of the ODE. Right? So the curve is such that at every point, this is the tangent. So you know the slope of the tangent at every point of that curve which you want to find. So once you draw the small line segments of the corresponding slope, you will have a direction field of the ODE. Okay. Now you draw smooth curves tangent to the line elements, and that is going to give you an approximate graph of the solution curve. Okay, so in this way you can plot the shape of the unknown solution just using this ODE, using this fxy on the right hand side. Okay, so the disadvantage of this method, so here you use it only in a very difficult situation where nothing else works, right? I mean, no easy method works. So if you have a closed form solution, then everything is nice, you just use it. when you can't find a closed form solution, and when you're sure that you can't find a closed form solution but you still need to get a hands on the solution, then you employ this kind of an approximate method, right? And as you can see, the way I described to you, the idea is easy, but you imagine we have to plot the slope of the tangent line at every point and then connect the draw curves such that these lines are tangential to the curve that we are drawing, and so on. So it's a tedious process, it's a time consuming process, and it does not provide you any formula for the solutions, right? It just gives you some shape of the graph, and just looking at the shape of the graph you can also predict where it will so what will be the value at some other point which we want to, right? So this is so in that way it's useful when you can't really write down a closed form solution. So which is why it's an approximate method. It is called the graphical method. So to illustrate this, let's introduce, so whatever we have just illustrated is what is called the method of isoclines. Before that, what is an isocline? The way I already described in the previous example, you had y prime equal to 2x plus y, and I said if you want to find the curve on which the slope of the tangent is 0, then you solve fx comma y equal to 0. If you want to find the slope, the curve on which the slope of the tangent is c, then you solve this, right? More generally, when you have fxy, this ODE, if you want to find the curve on which the slope of the tangent is c, then you look at the set of all xy such that fxy is c. Okay, you look at this set, okay, and on that set you know that the tangent has the same slope c, right? That curve is called isocline. Iso means same, cline means inclination. So the curve along which the tangent has the same inclination is called isocline, right? So in this example, this is an isocline for slope 0, this is an isocline for slope c, and so on, okay, along which they have the same slope. So if you choose different c, so you will have different, so you start with a c, then you look for the curve for which so you look for the curve in R2 along which the unknown curve has same slope, that's called isocline. So you do this for every c, and that you do by solving this. So once you fix a c, you solve so you look for all x and y such that this happens, which is the curve that you will obtain. So for each fixed c, you draw line elements with slope c, okay, and at each xy in the curve in the curve fx comma y equal to c. So as I said in the example, y prime 2x plus y, in this case fxy is 2x plus y. So you want to look for all curves such that the slope is 0, then it is some line which is y equal to minus 2x. So along these lines, the slope of the tangent is all 0. So that's what we mean by line element. So you draw this small line segments now, but you draw where the slope is this. Now let's say slope equal to 1. What about slope equal to 1? In this case it would be y equal to 1 minus 2x. right? So 1 minus 2x, so it is another line like this, and on this the slope is 1, so you draw slope is 1 at every point on this line. The slope is 1, that is the angle is 45 degree, right? So you see already you have some pattern here. The curve should come and touch like this, and here it should go like this, should come touch like this, it should go like this, should come touch like this, 0 slope here and 45 degree slope is like this. So you have some guess about the shape of the curve. Okay, that's what you do. So you do this for every C. So you start, so you first did for 0 slope, then 1 slope, 2 slope, so on. And if you keep doing this, you have actually plotted the shape of the graph. So you repeat this procedure for all C. Now you draw smooth curves, okay, and if you such that the line segments are tangent to the curve that you are drawing, then you have an approximate graph of the solution curve. Okay, so let's as an example, let's try doing it for this ODE. What is fxy here? Simplicity, it's x. Okay, so now what is the curve on which the slope of the tangent will be 0? It is on which fxy is 0, that is when x is 0. And when is x 0? X is 0 along the y-axis, right? So if you plot the R2, so x is 0 here, so on y-axis, you have the slope to be 0, which means you draw small line segments like this on the entire y-axis. Now what happens when when is the slope 1? Is 45 degree when x is equal to 1. When is x equal to 1? Along this line. So all your isoclines are actually vertical lines in this example. So the isocline where the slope is c is precisely the vertical line x equal to c. So in this line you see it's all slope 1. So if you keep doing this for each possible value c, then you would have plotted, for instance, when you want slope minus 1, you will have here, you will have slope minus 1 here. So if you proceed along like this, so you would have drawn all the isoclines of the OD which are vertical lines x equal to c, as I pointed out. Okay. Now if you plot this, you get a so what you have done here is you have plotted all the line segments of various slopes. So this already you see kind of gives you the shape of the, so this is the y-axis, minus not the y-axis where the slope is 0. So more or less your curve is coming like this and going. It's coming like this and going. Right? This is the kind of tangential here. Right? So that is how your solution curve seems to be, and that you can very easily verify here, right? Because in this case, if you integrate, it's x square by 2. Right, which are parabolas, and that's the kind of thing that you're getting here, parabolas, right? So this is the method of isoclines, right, where you use the ODE to plot the small line segments of corresponding slopes and use those tangent lines to draw the appropriate curve, right, which is called the integral curve. So, right, so we have the tangent line, so we are looking for the curves for which these lines are tangent, right, which is called the integral curve. So you plot the integral curves, then you have you have the graph of the solution. So whatever I have shown here, if you plot it, this is the solution that you will get. Okay, so this is the method of isocline. Okay, so I hope you understand. Now you take any example, various examples, try plotting. As I said, this is useful in cases where you cannot really get exact solutions, and you can, using this, you have a good guess of how your family of solution looks like, right? Okay. Now let's, so this will be the last lecture on first order differential equations. So far we have seen methods on how to solve differential equation. Now we will end the first order differential equation set of lectures with an application, okay, of how you can use the differential equation to actually find family of curves which are meeting, so two family of curves which intersect at some angle and so on. Okay, so let's start with the definition of what is called an oblique trajectory and orthogonal trajectory. So you have a one parameter family of curves which is fxy. Okay, a one parameter family of curves. Now the oblique trajectory of the given family of curves is any curve that intersects the given family at a constant angle theta, right? For instance, if I take, let's take R2. Let me take a simple example of, let's take the family of circles centered at origin. Okay, family of circles centered at origin of whatever radius. So it's a one parameter family of curves which are indexed by the radius. Okay, you have one parameter family of curves. Now suppose I want to look at all the family of curves which intersect this at say 90°, right? You see all straight lines, right? All straight lines passing through the origin. Okay, all straight lines passing through the origin will intersect the family of curves at any point at right angles. Wherever they intersect, the intersection is right angle, right? All these are right angles. So you have two family of curves. One is the family of curves which pass through origin, right? You have found, and then you have the family of circles, right? They both intersect at right angles. So this is what, and when they intersect, suppose you have two family of curves which intersect another curve which intersect at some angle which is not 90, then it's called an oblique trajectory. If they meet at right angle, it's called orthogonal trajectory. Okay, and you must already know that the intersection of two curves is defined as the angle between the tangent at the point of intersection, right? Let me draw some better. I don't know if I can draw some better curve. Let's see. So you see here, this is the tangent to this curve, and then you have a tangent to, oh, sorry, that is not a tangent. You have a tangent to this curve which is almost a straight line because the way I have drawn the curve. So the angle between the tangent is the angle between the curves, right? So at the point of intersection you draw tangents. The angle between the tangents is the angle between the curves. So that is how you define the angle between the curves. So you can have, so once you have a family of curves, you can always ask this question: what is the family of curves which intersects the given family of curves at some angle theta? at every point of intersection. Okay, it's a constant angle theta. So as the example that I gave as such, so if you have a family of circles centered at origin and radius c, okay, then every straight line through origin is an orthogonal trajectory of the family of circles, the way I showed you some time back. Okay, so these two family of curves intersect at right angles at every point of intersection. Okay, the converse is also true. Each circle is an orthogonal trajectory of the family of straight lines, right? It's because if they intersect, both curves intersect each other at the same angle. Okay, so now the question is, how do I, given a family of curves, how do I find, and given some angle theta, let's say we are given some angle theta, can I find the family of curves? Let's call it G. For F, we call it G. Okay. Can I find the family of curves Gxy d equal to 0 such that they intersect at angle theta? Okay, and that's where differential equation comes in. So for that, what you do, you are given a family of curves, you differentiate with respect to the x variable and eliminate the constant, which is the parameter that you have, and you obtain a one parameter family of ODE. Okay, so you differentiate, eliminate the constant, you are going to get a one parameter family, you are going to get an first order ODE. Okay, so this ODE, and this ODE has an information. What is this information? This ODE is telling you that the slope of the tangent is fxy. Okay, and what you want is another curve which should intersect this at an angle theta. So y prime fxy gives the slope fx of the integral curves at xy. Okay, now you are looking for, so what is the angle of inclination, because the slope is f, so which means the angle of inclination of the tangent line is tan inverse of f, right? Right, so that is the angle of inclination. So you have a family of curve. So let's take one curve, okay, and at that point, this ODE is giving you the slope at every point. So let's say this point. So at this point, the slope is fxy, which means the angle made is tan inverse of fxy. Now, if you are looking for another curve which intersects this curve at an angle theta, which means this angle should be theta, then what is the inclination of this tangent line? The inclination of this tangent line is the inclination of this tangent line plus theta. Okay, right? The inclination of this tangent line is inclination of this tangent line plus theta, because that's how we have fixed this, right? So the tangent line that of the oblique trajectory that we are interested in, right, will have the inclination tan inverse of f plus theta. Okay, so if that is the inclination of the tangent line, what is the slope of that? Tan of this, right? So the slope of the tangent line that of the trajectory that we are interested to find, which will intersect at an angle theta, is tan of this. Now this is tan A plus B. Use the formula for tan A plus B, which is tan A plus tan B, 1 minus tan A tan B. Okay, so this is the slope of the tangent line of the curve that we are going to find, which will intersect the given curve at angle alpha, at angle theta. Okay, so now how do you find that curve? How do you find the curve whose tangent line is, whose tangent line has the slope given by this? So you want to find a curve whose tangent line means y prime should be equal to this quantity. So you solve this ODE, y prime is equal to this quantity. If you solve this ODE, you are going to get a one parameter family of solution, which will be the curve that you are interested in. So this gxy comma c is the curve which will intersect, is a family of curve which will intersect the given family of curves at angle theta. Right? In this case, theta is not 90 degree, right? Not pi by 2 because of so here when we say theta, I am looking at the you can look at the range minus pi to pi, that is 2 pi, right? So we are looking at the range minus pi to pi, let's say, okay? Or you can even look at 0 to 2 pi, doesn't matter, whichever, you just fixed a 2 pi period, okay? So now for orthogonal trajectory, your so because if fxy is the slope of the given curve, then the orthogonal, so the slope of the tangent which is intersecting it at 90 degree will be minus 1 over fxy. So that is going to give you the orthogonal curves, orthogonal family of curves which will interest of this family of curves, right? It will give the orthogonal curves corresponding to the given family of curves. So this is how you find oblique trajectories and orthogonal trajectories. If we look at examples, you will understand much more. Okay, this is just to explain the theory behind it. So what are the examples? So let's look at the same example that we have seen, but now we will actually show that the lines passing through origin is orthogonal to the family of circle and vice versa. So you take the family of circles centered at origin. Okay, now what should we do? As per the algorithm, we should differentiate this and eliminate the parameter c. So you differentiate this, so you get this, which is going to give you this ODE. So your fxy is minus x over y. So the slope of the given curve, so the slope of the tangent of the given curve is minus x over y. Now you suppose you want to find the orthogonal family corresponding to the given curve, then that should be given by the ODE y prime. So fxy is this, I have done minus 1 over fxy here, right? Minus 1 over fxy is precisely this, right? Now this ODE you can solve. This is in the separable form, right? This is a separable form, you can solve. So what you get is a one parameter family of curves, which is lines passing through origin of all possible slope, right? So this way we have shown that this is the orthogonal family. You can also do the other direction. Okay, in this case, because in this case you notice that this vertical line x equal to 0 is not obtained here, right? That is because of when you put x at the bottom here, you have ignored the fact, you have thrown away the fact that you have put in the condition that x not equal to 0, right? So from here you get all straight lines, but even the vertical line is also included in the family of curves, and that you only have to observe it separately. Okay, so basically what I am trying to emphasize here is that after doing this, you ensure that the cases that you ignored also do not satisfy the condition that you're looking for. If it does, you include that also in this family of curves. The way it's happening here, x equal to 0 is excluded here when you did this, but finally it is also a possible curve which will intersect the given curves in at 90 degrees. Okay, now let's look at another example. Okay, let's take this family of parabolae indexed by c here. So what should you do as per algorithm? You differentiate it and eliminate the constant, eliminate the parameter c. So So you differentiate it, you get y prime equal to 2cx, and you have y equal to x square. So you use this information here to eliminate c. So you eliminate c between the ODE and the family of curves. So c is y over x square. Use this information here. So you get this ODE. Okay. Now suppose I am looking for the family of curves which intersect this parabola at right angles at 90 degree. Then this is fxy, so I should do minus 1 over fxy. So if we do that, we get this ODE. Okay, and this is already in the separable form. You can solve it. You solve, you get a one parameter family of curves which are family of ellipses. So the orthogonal family for this family of parabolae is the family of ellipses. Okay, now these are ellipses centered at the origin and x-axis being the major axis. Okay, so this is one application of differential equation, right? You have a family of curve, you look at the ODE for which this family of curves are the solutions, and use that information to write down the other family of curves which intersect them at a given angle. Okay, now both the examples that we have done is for 90 degree. Let's do an oblique trajectory example. So consider the straight line passing through origin of all possible slopes. So let's try finding the family of curves which intersect the straight line at the angle 45 degrees. Okay, so what do you do? As per algorithm, you differentiate. You have differentiated. Now we have to eliminate the parameter m. Okay, use this information here to eliminate m. So m is y over x. So what you get is y prime is y over x. Okay, so your fxy is y over x. Now what you should do, use this fxy, and your theta is 45 degree. You already have derived the formula that you need to. So fxy tan 45, this gives you this. Okay, now use that. Now use this as a right hand side in an ODE. So you solve this ODE. Okay, this is the ODE that will give you the family of curves which will intersect the given family at the angle 45 degree. Right, now this ODE is homogeneous. Right, you can, right, they are homogeneous. Both numerator and denominator have the same homogeneity degree, and they cancel out. So it's homogeneous, and so it's a homogeneous ODE. So you use this y over x is equal to z change of transformation, which will convert the homogeneous ODE to a separable ODE. Okay, so you have a separable ODE here. You solve the separable ODE. So when you solve the separable ODE becomes, this is a separable ODE that you have here from the previous slide here. Right, whatever we have here, bring the minus z here, accumulate all z on one side and x on other side, you get this. Now you integrate both sides, you get in terms of log, simplify them, you will have this one parameter family of curves, and this is precisely the family of curves which will intersect the straight lines passing through origin at angle 45 degrees. Okay, so this is how you go ahead and do it. So with this we have completed the first order differential equations. From the next lecture we will start looking at higher order differential equation. Okay, mostly we will concentrate on second order, but wherever the technique applies to any higher order other than second, we will show that aspect. Okay, see you in the next lecture. Thanks a lot. Bye.